Before diving into hash tables, let's first review the pros and cons of some simpler data structures, starting with arrays. Recall that arrays allow us to store elements of a single data type contiguously in memory. Because each element is associated with an index or location, we have random access to all of the elements in an array. In other words, we can access any element in a single step by indexing into the array. This is a big deal because algorithms like binary search depend on random access. A downside of arrays is that their size is fixed. Because arrays store data contiguously in memory, you must specify an array's size when you declare the array. You are effectively asking the operating system to reserve the appropriate amount of memory for the array's elements. There's no guarantee that more memory adjacent to your array will be available for use later, so arrays cannot easily grow. Recall that we also learned about linked lists, which can grow because their elements are not contiguous in memory. Each node in a linked list contains the element we want to store, as well as a pointer to the subsequent element in the list. Unfortunately, the price we've paid for dynamic size is random access to elements. In order to access a certain element, it's necessary to traverse the entire list until the desired element is reached. So if I'm looking for the number 9, I'd follow the pointers from node to node, checking whether the value of each node is equal to 9. As such, in the worst case, lookup is O of n, which is far from efficient. Can we do better than O of n while still allowing our data structure to grow over time? Hash tables offer a solution. Hash tables are used when speedy insertion, deletion, and lookup of elements is priority. In theory, insertion, deletion, and lookup can even be accomplished in constant time. So what is a hash table anyway? A hash table is just an array coupled with a function, which we'll call the hash function. The hash function takes a piece of data as input, we'll call this a key, and outputs an integer commonly referred to as a hash value. The hash value maps our key to a particular index in the hash table. You'd initially use the hash function to determine where in the hash table to store a given key. Later, you'd use the same hash function to determine where in the hash table to search for a given key. For this reason, it's crucial that a hash function behaves consistently and outputs the same hash value for identical keys. Know that hash tables can be used to store data of all types, but to simplify things, we'll focus on strings for now. Here's a simple hash function for strings. This hash function computes a hash value based on the first letter of the key. Apple begins with the letter A, so it's mapped to index 0 of the hash table. Similarly, banana is mapped to index 1, and cat is mapped to index 2. If a friend asks if the word dog is in the table, we'll input dog into the hash function, which will output a hash value of 3. Since dog is not stored at index 3, we can say with confidence that dog is not in the table, even though we've only checked one of the hash table's 26 indices. Time to throw a wrench into things. What if we want to store ant into the table as well? Ant hashes to index 0, just as Apple did. This is an example of a collision, the result of two keys hashing to the same index. Even if your hash table is larger than your dataset, and you've chosen a good hash function, you still need a plan for dealing with collisions, if and when they arise. Let's discuss the pros and cons of two common methods for resolving collisions, linear probing and separate chaining. With linear probing, if a key hashes to the same index as a previously stored key, it is assigned the next available slot in the table. So ant is now stored at index 3, since indices 0, 1, and 2 were already in use. And if we try to store a third word that starts with the letter A, it's assigned to index 4, since indices 0, 1, 2, and 3 are full. As you can see, even from this simple example, once a collision occurs, you significantly increase chances that another collision will occur in the same area. This is called clustering, and it's a serious drawback to linear probing. Moreover, worst-case insertion, deletion, and lookup times have devolved to O of n, as the next available slot could potentially have been the last slot in the table. maybe separate chaining will offer a more compelling solution. In the separate chaining model, the hash table is actually an array of pointers to linked lists. When a collision occurs, the key can be inserted in constant time at the head of the appropriate linked list. What happens now when we search for Apple in the hash table? In the worst case, we must traverse the entire linked list, starting at index 0. The worst case lookup time for a hash table that uses separate chaining is therefore O of n over k, where k is the size of the hash table. Wait a second, k is a constant, so O of n over k is really just O of n, which was the worst case lookup time for a linked list. Have we really gone through all the trouble of learning about hash tables only to end up back where we started? That may be the case from a theoretical perspective, but in the real world, O of n over k could be a huge improvement over O of n. Think of it this way. Assume that k is 10. Would you rather wait 100 seconds or 100 over k, 10 seconds, for Microsoft Word to finish spell checking your document? As you just saw, resolving collisions entails one form of linear search or another, which slows things down considerably. Therefore, you'll want to choose a hash function that minimizes the chance of collisions occurring in the first place. Here are some properties of good hash functions to keep in mind. A good hash function should make use of all information provided by a given key in order to maximize the number of possible hash values. For example, if we had two strings, cat and caterpillar, we'd want them to hash to different places on the table. If our hash function only took into account the first 1, 2, or even 3 letters of the strings, a collision would occur, since both words start with the same 3 letters. Hash values should be spread evenly across the hash table. This will reduce the length of linked lists, should collisions occur. It's also a good sign if your hash function is capable of generating very different hash values for similar keys, making collisions much less likely. Our goal is speedy insertion, deletion, and lookup. The hash function plays a crucial role in each of these processes and will be called very frequently. Therefore, make sure it employs only very simple, quick operations to minimize runtime. I hope you've enjoyed this brief introduction to hash tables. My name is Lauren, and this is CS50.